Hello everyone, welcome to Monkey Tales. We are here with a Pulley problem. Surprisingly, this is not a standard Newton's laws of motion force problem, but rather a relative motion. To start, the problem reads as follows. There are three blocks A, B, and C, which are suspended with the help of three pulleys and two threads with equal horizontal separation between adjacent blocks. That means we have three pulleys in our system, and the blocks are hanging initially in such a way that the horizontal separation between them is same. Let's assume it to be L. And it's said that the blocks are initially at the same level and rest. They are released from the same line and following constraint as follows. 1. All the blocks are in the same line. Second, we are given that velocity of B with respect to A is 4 cm per second falling downwards. We also have a third constraint that we would call the line constraint or length constraint. Okay, to start with the problem, we'll first assume that the block A is moving upwards and has moved a displacement of magnitude A. Similarly, block B has suffered a displacement of magnitude B, and block C has suffered a displacement of magnitude small c. If the block A is moving in certain direction, this pulley would also move in an equal and opposite direction. So it must have suffered a displacement of magnitude A, but in an opposite direction. The first constraint is all the blocks are in the same line after this motion. So let us plot a small diagram where the first block A has moved distance A. This is the initial level. The block B has suffered a displacement B downwards, and block C has suffered a displacement of magnitude C. We are also given these separations to be small l. For these points to be in same line, we can use the slope formula, that being the slope of this line should be equal to the slope of this line. We can plot an arbitrary coordinate system where the block A was initially at 0, 0, meaning the block A is currently at 0, A. Block B was at 0, is finally at L, minus B, and block C is at 2L, minus C. So our slopes are A plus B by 0 minus L is equal to minus B plus C L minus 2L. These would return minus L, so we would simply cancel them out, and we would be left with 2B is equal to C minus A. Now from the definition of velocities, we can also say that VA equals dA by dt, VB equals dB by dt, and VC equals dC by dt. Using this, we would obtain 2VB is equal to VC minus VA. This is our first equation. Similarly, we can obtain a second equation. We are given a second equation that the relative velocity of B with respect to A is 4 cm per second. For the relative velocity, since VB and VA are assumed to be in opposite directions, we can write the equation VB plus VA is equal to 4 cm per second. And the third equation that we obtain is from the length constraint. Notice that since these are tethered together by a finite string, the length of these strings are never going to change. So with respect to this pulley, since this pulley has moved displacement A and this block C has moved net displacement of C, the length change in this direction must be C minus A. Similarly, the length change in this direction, which is downward, length change in this direction should be A minus B upwards or B minus A downwards. For the string to be finite, we must say that A minus B should be equal to C minus A. That is 2a equals b plus c, and hence 2va is equal to vb plus vc. Solving these equations, you can find out the final solution. The interesting part about this question is that normally we consider the pulley problems as a part of force related questions or Newton's laws of motions, but surprisingly this is a question related to relative motion and did not ever require any concept of force. See you in another video.